All right, in this video, we're going to look at molecular orbital descriptions of cycloadditions. Now, Diels-Alder reactions are, of course, examples of cycloadditions, so we're really continuing our discussion of Diels-Alder reactions. Okay, so let's consider the molecular orbital description of a Diels-Alder reaction. Now, when we talked about Diels-Alder reactions, we said this reaction wasn't very efficient without an electron withdrawing group on the dienophile. But to simplify our MO picture, we're just going to consider sort of this simplest Diels-Alder reaction. When we talked about MO theory before, we talked about the fact that the frontier orbitals were very important for chemical reactivity. The frontier orbitals are the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And so we're interested in these frontier orbitals in both the diene and the dienophile. Now, generally, what happens when we add an electron withdrawing group to the dienophile, right? It becomes greedy for electrons, right? That electron withdrawing group means it's short on electrons, and so it's ready to accept new electrons. So generally, the way the reaction happens in a Diels-Alder reaction is the electrons from the highest occupied molecular orbital of the diene are transferred to the lowest unoccupied molecular orbital of the dienophile. Now, a really important requirement for these cycloaddition reactions is that the phases of the reacting molecular orbitals must be symmetrical. So we've sort of drawn the diene in a dienophile like their regular shapes, but then I've also drawn, right, this is the HOMO of butadiene, the diene, and the LUMO of the dienophile of the ethylene. And so, right, we've got two red on top, two blue on top, so these are the two red and the two blue. And then we've got red on one side and blue on the other side for the dienophile, red on one side and blue on the other side. So in the case of a 4+2 addition, right, in Diels-Alder reactions we have 4+2 addition, the HOMO of the diene lines up symmetrically in terms of the symmetry of the orbitals with the LUMO of the dienophile. And so we get constructive interference, and so we can go ahead and form these new sigma bonds. And so we do get 4+2 cycloadditions in the case of the Diels-Alder reaction. But we won't always see this proper symmetry. And so only when there is conservation of orbital symmetry is the reaction considered symmetry allowed. And so the 4+2 addition of the Diels-Alder reaction is a case where it is symmetry allowed, and so that's why we see this particular cycloaddition. Right? But it's not always the case that cycloaddition is symmetry allowed. And so let's consider another example. We're going to consider 2+2 addition. So now we have an ethene and an ethene, right? 2+2 addition. In this case, we would make cyclobutane. And so now, you know, both the diene and the, well, I guess it's not a diene anymore, but both reactants are ethene. And so we're interested in the highest occupied molecular orbital of ethene and the lowest unoccupied molecule of ethene in the other molecule. And again, we're going to see, can we get this donation? So here are our HOMOs and LUMOs that we're interested in for the two molecules again. Right, but now in this case, the HOMO of ethene and the LUMO of ethene don't match up symmetry-wise, right? We get constructive interference when these two orbitals want to overlap, but we get destructive interference when these two overlap. And so in this case, we don't get cycloaddition. And so this is why the symmetry of the orbitals is very important, and why we see some cycloadditions, like the 4+2 of the Diels-Alder reaction, but at least without help, we don't see the 2+2 cycloaddition of an ethene plus an ethene. Now, this doesn't mean that 2+2 cycloadditions are impossible. And this ties back into something else we talked about when we were talking about molecular orbital theory. And that is the fact that transitioning electrons from the HOMO to the LUMO can often be achieved by exciting one of the electrons with a photon of electromagnetic radiation. And so if we hit our ethene, or one of the ethenes anyway, with the right frequency of electromagnetic radiation, we can cause one of the electrons from the HOMO to jump up into the LUMO. Well, then now that changes things, because now we're in an excited electronic state of ethene, and now what was the LUMO, because it was unoccupied, now has an electron in it, and so now it is the highest occupied molecular orbital. So now, when we compare the excited state of ethene, right, where we have an electron in what was the LUMO, and then as long as we haven't excited the other ethene molecule, right, its LUMO is still the same, and so now the HOMO of the excited ethene matches up symmetry-wise with the LUMO of the other ethene, and we can get 2+2 cycloaddition. So in this case, we would call this a photochemical pathway. So without hitting these guys with the correct frequency of electromagnetic radiation, the reaction can't happen. But if we can hit it with the right frequency of electromagnetic radiation and cause this photochemical reaction to happen, then we can get the 2+2 cycloaddition. Now, this photochemical pathway was not necessary in the case of the Diels-Alder 4+2 cycloaddition, because the HOMO and the LUMOs of the diene and the dienophile already had the correct orbital symmetry.